Daniel Bernoulli, a Swiss mathematician, was born January 29, 1700, in Groningen, Netherlands. He was a second-generation mathematician of the Bernoulli family. At only the age of 7, Daniel loved to study mathematics, but his father only wanted him to study business. Daniel went on to study many fields including medicine, biology, physiology, mechanics, physics, astronomy, and oceanography. Bernoulli is most notably known for his book that he had written in his late 30s called Hydrodynamica. Published in 1738, this book shows Bernoulli's study of how fluids flow in a pipe system, also including how things such as pipe diameter and height affect the pressure and velocity of flowing fluids. With this being said, we can use Bernoulli's equation to solve for the variables such as height, velocity, and pressure at certain points throughout the pipe systems. But what does this equation look like? As we can see here, the equation is P plus 1/2 rho V squared plus rho GH equals constant. The equation states that the sum of these three terms remains constant along a streamline. Each of these terms is a pressure. The first term is a static pressure, which is just the pressure P of a fluid. Then we have dynamic pressure, which is a function of the fluid density, rho, and velocity, and represents the fluid kinetic energy per unit volume. And the last term is hydrostatic pressure, which is the pressure exerted by the fluid due to gravity. G is the gravitational acceleration, and H is the elevation of the fluid, which is just its height above a reference level. Bernoulli's equation can be very useful in many different situations. For example, if you have a pipe at the same height but a change in diameter, you can rearrange the equation in such a way that you can solve for the pressure change due to the change in diameter. As you can see, we can cancel out the hydrostatic pressure because the height does not change, and all we are left with is static and dynamic pressure. We can now rearrange what is left of the equation so that we can solve for the change in pressure. But in order to do this, you also need to know the equation that is called the continuity equation, also known as conservation of mass formula, which states that the mass flow rate is equal to the product of the fluid density and the pipe cross-sectional area. With this equation, we can rearrange it in such a way that we can solve for the velocity at point 2 and plug that velocity back into Bernoulli's equation to solve for the change in pressure. With this equation, it can prove how velocity and pressure are inversely proportional to one another, which is also stated in Bernoulli's principle. Bernoulli's principle states that for horizontal flow, an increase in velocity must be accompanied by a decrease in pressure. This means the faster a fluid is flowing in a pipe, the less pressure that will be exerted on that fluid. As you can see, Bernoulli's equation can be very useful when trying to determine the velocity, pressure, and height of fluids in a pipe. But there are a few key points or rules you must take into consideration when attempting to apply Bernoulli's equation. The first rule is that the flow of the fluid must be laminar and steady. This means that there can be no turbulence in the fluid that would cause it to become unsteady. The second rule is that the fluid must be non-viscous, which means that the viscous forces caused from the fluid is negligible compared to the pressure and inertial forces. And finally, the third rule is that the fluid must be incompressible and having a constant density. This is usually fine for liquids, but the issue arises when you have air. All three of these rules must be taken into consideration when trying to solve for variables using Bernoulli's equation. Thank you for watching. Hope you enjoyed.